Let's solve some more problems in applying Leibnitz theorem. Okay, let's start with the sixth one. Y equal to log x plus square root of 1 plus x square the whole square. Show that 1 plus x square yn plus 2 plus 2n plus 1 yn plus 1 plus n square yn is equal to 0. Again, here itself we know we have to do differentiation twice before applying the Leibniz theorem. So let's do the differentiation. Okay, now this looks very complicated. Just take it step by step. Take the exponent first. So 2 log, everything else remains as it is. Okay, 2 minus 1, 1. Now take the next one, log. So log is nothing but 1 by x plus square root of 1 plus x square times. Now let's take the innermost bracket. So that will be what? Within brackets 1 plus square root of 1 plus x square. So that will give us what? 1 by 2 will come down, and what we'll have is square root of 1 plus x square to the power of 1 minus half, that is minus half. Yes, and then finally the innermost under the square root whatever is there. So 2x. So this is the differential of y. Okay, now let's do some simplifications. 2 log x plus square root of 1 plus x square, and then 1 by x plus square root of 1 plus x square, and here let's take LCM. This basically goes down because it is minus half. We can take it to the denominator, so we can take it as square root of 1 plus x square. Okay, this 2 and 2 gets cancelled, and let's take the LCM, 1 plus x square. So this also becomes 1 plus x square plus x. This and this are same, so they get cancelled out, and what we have is this term, the denominator, we can bring it to the left hand side. So square root of 1 plus x square y1 is equal to 2 log square root of 2 log x plus square root of 1 plus x square. I want to remove this square root, so let's square it off. So if we square it off, what do we get? The square root goes off, this becomes y1 square, this becomes 4, this becomes log x plus root of 1 plus x square the whole square. Yes, which is what exactly y is. So which means we can make this as 4y, and this remains 1 plus x square y1. So now let's differentiate it once more. Remember, we have to differentiate it twice. So looks very similar to the previous problem, but remember the starting point was different. There we started off with sine inverse, and here we started off with log. Okay, let's differentiate it. 1 plus x square as it is, and y1 we will differentiate it, so this will become 2y1 y2 plus, now we will differentiate, y1 remains as it is, and we differentiate 1 plus x square, so which we get 2x equal to 4 remains as it is, y becomes y1. Now let's rearrange this. Not only that, 2y1 is common to all of them, so let's divide it by 2y1. So we are left with 1 plus x square, 2 gets cancelled, y2 plus 1 y1 will go off, 2 will go off, we are left with y1x minus, let's bring it to the left hand side. Let's bring it to the left hand side. So 2y1 gets cancelled. So we are left with minus 2 equal to 0. Now let's apply the Leibniz theorem to each of these terms. Let's apply it to this first. NC0, let's say y2 is the u function. So in which case un will be what? Y n plus 2, because 2 twice we have already done. And v, that remains as it is. So x square plus nc1. Now nc1 u n minus 1. So n minus 1 means what? N plus 1 instead of plus 2. And v1 would be what? Differentiation of 1 plus x square. So that is 2x plus nc2 yn times 2. Now let's take the next term, y1x. So nc0 un of y1. So which means what? Yn plus 1. Once it's already been done. X as it is. Then nc1 yn and then 1. If we differentiate minus 2, it gives us 0. So we ignore it. Now let's simplify it. nc0 is 1. So yn plus 2, 1 plus x square plus nc1 is nyn plus 1. The 2x we can bring it to the front, plus nc2 is n times n minus 1 by 2 times 2yn. This 2 gets cancelled, plus nc0 is 1 again. So yn plus 1, x we bring it to the front. Here it should be actually plus. Now nc1 is n yn equal to 0. Now again simplify it. These two are like terms and this two are like terms. So 1 plus x square yn plus 2 plus like terms. Let's add them. What is common? Yn plus 1 is common. So what are we left with? Here x times yn plus 1 is common. So 2n plus 1, we take it out, xyn plus 1 plus within brackets n square minus n plus n yn equal to 0. So finally we are left with plus 2n plus 1 xyn plus 1 plus n gets cancelled. So we are left with n square yn equal to 0. Now this is what we had to show. Okay, cos inverse of y by b is equal to log of x by n to the power of n. Okay, now what do we do? How do we go about it? Okay, of course, show that x square y n plus 2 plus 2n plus 1 x y n plus 1 plus 2n square yn equal to 0. So how do we begin? Let's now remember we have to take derivative twice before applying the Leibniz theorem. But before that, let's try to simplify it. So y is equal to cos inverse will become cos log of x by n to the power of n. Now we are left with y by b. So that b comes here. And again log property, it will become n log x by n. Now let's take the first derivative. So 1 is equal to b as it is. Cos is sine n log x by n times. Now we take the differential of this. So that will give us n times n by x times then the differential of x by n, so which is 1 by n. So n gets cancelled and we end up with y1 equal to minus b sine n log x by n times n by x. Now this x can go to the other side and this n, let's bring it to the front, minus n b. Okay, let's differentiate once more. X y2 plus 1 times y1 equal to minus n b. Now sine will become cos if we differentiate it. Cos n log x by n times, now we take the differential of n log x by n. N log x by n would be n times n by x, and then the differential of x by n. X by n is 1 by n. So this n gets cancelled and this x can be brought to this side. So we end up with x square y2 plus x y1 is equal to minus nb cos n log x by n, and this n we can bring it to the front, so it becomes n square. Now remember, n log x by n cos, or rather b cos n log x by n is nothing but y. This entire thing is y. So this becomes minus n square b, no, not b, n square y. Now we apply the Leibnitz theorem. Okay, NC0, let's say y2 is u, so un yn plus 2 and x square as it is, plus nc1 yn plus 1 and 2x plus nc2 yn times 2. Okay, next time when we take the differential of 2, it will become 0. So we stop. So this is done. Now we take up this. So plus nc0 yn plus 1 and x plus nc1 yn and 1 is equal to minus n square, y is yn. Now let's simplify. This is 1, so yn plus 2 x square plus n times yn plus 1, let's bring in 2x in front, plus 2 times, no, let's do it. Okay, 2, let's bring it front. nc2 is n into n and yn, okay, plus nc0 is 1, so this becomes x yn plus 1 plus nyn, and let's bring it to the left hand side, so plus n square yn equal to 0. X square yn plus 1 plus, now these two are like terms, so what's common? 2n plus 1 is common, x yn plus 1 is common, so we take out 2n plus 1. Okay, then this and this, all three are like terms, so plus, let's take out, so 2n times n minus 1 plus n plus n square equal to 0. X square yn plus 1 plus 2n plus 1 xyn plus 1 plus now 2n square, this becomes 2n square minus 2n. Minus 2n plus n is minus n. 2n square plus n square. 1 second. Now this 2 is not required here. Why? Because this would have got cancelled here. I missed that. Okay, so now this becomes n square minus n plus n square. X square yn plus 1 plus 2n plus 1 xyn plus 1 plus these two gets cancelled. 2n square yn equal to 0. So this is what we had to show. Okay, now see, remember, after applying the Leibniz theorem, it's mostly algebra, and this is where we usually end up making mistakes, right? Okay, let's take the next one. Y to the power of 1 by m plus y to the power of minus 1 by m is equal to 2x, and based on this we have to show that x square minus 1 yn plus 2 plus 2n plus 1 xyn plus 1 plus n square minus m square yn equal to 0. Okay, let's say y 1 by m is equal to, or rather let's say z is equal to y to the power of 1 by m. Now remember, y to the power of minus 1 by m is nothing but 1 by y to the power of minus 1 by m. So which means y to the power of 1 by m is 1 by z. Okay, so which means our equation becomes z plus 1 by z is equal to 2x. Let's take the LCM. Z square plus 1 is equal to, and that z will come to this side, and if it bring it to this side, it becomes minus 2xz equal to 0. Let's rearrange this. Plus 1 equal to 0. Now remember, this is a quadratic equation. So how do we find z? Remember, this is a quadratic formula, so we have to apply the quadratic equation to find z. So z is equal to minus b. So minus 2x plus or minus square root of b square minus 4ac. B square is minus 2x minus 4 times 1 times 1 divided by 2a, that is 2 times 1. Now this becomes 2x plus or minus 4x square minus 4 divided by 2. 2x plus or minus, now 4 is common, so we can take it out of the square root. So we are left with x square minus 1 by 2. So now 2 gets cancelled and we are left with x plus or minus x square minus 1. Now let's take the positive sign. And remember, our y to the power of 1 by m is equal to what? Now remember, z was this, but now we know z is x plus or minus square root of x. So x plus, let's take the positive. Now we want y equal to, so 1 by m in the exponent will become what? Here it will become m. Right? So remember, x to the power of 1 by 2 is nothing but, if we take it to the other side, it will become y square. So similarly here, y is equal to x plus square root of x square minus 1 to the power of m. We have it in y equal to form. So now we can differentiate it. M x plus square root of x square minus 1 remember exponent first, so m minus 1. Now within the bracket whatever is there, we differentiate that. So that becomes 1 plus a square root will become what? Now this is nothing but x square minus 1 to the power of 1 by 2. So 1 by 2 x square minus 1 to the power of 1 by 2 minus 1. So that means what? Minus 1 by 2. Yes. Times, now inside the square root whatever is there, and that is 2x. Okay. So now m x plus square root of x square minus 1 m minus 1 times this 2 gets cancelled, square root of x square minus 1 times x. So this becomes x. Let's take the LCM. Square root of x square minus 1 plus x by x square minus 1. Now this denominator can come to this side. So x square minus 1 y1 is equal to m times x plus square root of x square minus 1 to the power of m minus 1 times x square minus 1 plus x. So they are basically both same. So it becomes m minus 1 plus 1, which is nothing but m. And we know what? That this itself is nothing but y. So m y. Now we differentiate it once more. So when we differentiate it, what happens? X square minus 1 y2 plus, no, just to make it much more simpler to differentiate, let's remove the square root. So we square both the sides. So square both the sides. So this becomes y1 square equal to m square y square. Now we differentiate. X square minus 1 times 2y1 y2 plus now 2x y1 square is equal to m square 2y y1. Now here 2y1 is common, so we divide it by 2y1. X square minus 1, 2y1 goes off, so we are left with y2 plus 2 disappears and one of the y1 disappears, so we are left with xy1 plus, okay, let's bring it to this side, so it becomes minus n square, 2y disappears, so we are left with y1. Now we apply the Leibniz theorem. Why do we do that? To make it, to get yn, nth derivative. So let's now apply the Leibniz theorem. NC0. Now you might be wondering why I keep writing the same statement again and again. Why don't I jump steps? The chance of making mistakes is very high. So let's say y2 is our u and this is our v. So yn plus 2, because we have already differentiated twice, and v, so that is x square minus 1 plus nc1. Now keep reducing y, so n plus 2 minus 1 is n plus 1, and we need to differentiate this v1 plus nc2 yn, and it becomes 2. Next time when we differentiate, it will become 0 and the term itself will become 0. So we stop. Now we take up the next term. So nc0 y n plus 1, because it has already been differentiated once, and x plus nc1 yn and v1, that is 1 minus m square, and this will become yn plus 1 equal to 0. Okay, now simplify. nc0 is 1, so x square minus 1 yn plus 2 plus nc1 is n, yn plus 1, so 2x we can bring it in front, plus 2 in front, n times n minus 1 by 2, so 2 gets cancelled, yn plus nc0 is nothing but 1, xyn plus 1 plus nc1 is n yn minus m square yn plus 1. Okay, now this and this are like terms, and this is also like term. This and this is like terms. So now x square minus 1 yn plus 2 plus n plus 1, 2n plus 1 and minus m square. Yn plus 1 times x is, no, x is not common here. So do you notice, if you remember, show that was quite a long time back. Okay, here it should only be 2n plus 1 and m square should go with yn, whereas here we are getting with n plus 1 m square. So that means there's some mistake we have made. Now what's that mistake? Now we go backwards. So this should be yn. Why is this yn plus 1? Because here it is yn plus 1. And why is this? Because of this. Now this should actually be what? Y. Because then only this will become yn. Okay, here I have made a mistake. So I have cancelled y instead of y1. We are dividing it by y1. So 2y. So this and this gets cancelled and we are left with y. So if that is y, this is n. yn. And this is yn. So if that is yn, then that is not a like term with this. It is a like term with this. So which means 2n plus 1 yn plus 1, or rather xyn plus 1. xyn plus 1 minus n square minus n square minus 1 n plus n minus m square yn equal to 0. X square minus 1 yn plus 2 plus 2n plus 1 xyn plus 1 minus these two gets cancelled and we are left with n square minus m square yn equal to 0. And this is what we had to show. Remember, if you, while solving a problem, you should realize you have made a mistake as early as possible. So that means, you need to keep your mind open. Okay, so let's look at the next problem. That is, I think, 9th one. Okay, so y is equal to a cos log x plus b sin log x, and show that x square yn plus 2 plus 2n plus 1 xyn plus 1 plus n square plus 1 yn equal to 0. By the way, this most of the problems we have seen show that comes in this pattern itself, and that is because of the Leibnitz theorem. Okay, so let's differentiate. Cos is minus sine, so a sine minus a sine log x, and then log x differential is 1 by x, plus sine is cos, so b cos log x times 1 by x. So x is anyhow common, so we can bring it to this side, xy1, and we are left with a sine log x plus b cos log x. Okay, now let's differentiate once more. And we know how many times we have to differentiate because of this. Okay, let's differentiate once more. X y2 plus y1 is equal to, sign is cos, so a cos log x times 1 by x. Cos is minus sign, so minus b sine log x times 1 by x. Again we bring x to this side, so it becomes x square y2 plus xy1 equal to, let's bring minus out. So if we take out minus, we are left with what? Cos log x plus sine log x. Cos log x plus sine log x. A and b is also there. So this is nothing but y. So we can bring it to this side, x square y2 plus xy1 plus y equal to 0. Now we can apply the Leibniz theorem. NC0, let's say u is y2. So yn plus 2 x square plus nc1 yn plus 1. Keep reducing y by 1 and keep differentiating v. So this becomes 2x plus nc2 yn and 2. Next time 2 will become 0, so term will become 0. Okay, now let's take the second term. nc0 x y n plus 1 plus nc1 y n times 1 plus y n equal to 0. 1 y n plus 2 x square plus nc1 is n y n plus 1 2x plus nc2 is n times n minus 1 by 2 yn times 2. So 2 gets cancelled plus 1. So x y n plus 1 plus n times y n plus y n 0. X square y n plus 2 plus this and this is common. So like terms. So 2n plus 1 x y n plus 1 plus this becomes n square minus n. So this and this. N square minus n plus n plus 1 yn equal to 0. These two gets cancelled and we are left with n square plus 1 yn equal to 0, which is what we had to show. And let's say one final problem. Y equal to e to the power of n sine inverse of x. Show that 1 minus x square y n plus 2 minus 2n plus 1 x y n plus 1 minus n square plus m square y n equal to 0. Okay, let's differentiate. We have to do differentiation twice. So y1 equal to e to the power of m as it is, that is with sine inverse of x, and then the exponent we have to differentiate, that is m by sine inverse of x is 1 minus x square. This square root of 1 minus x square can be brought to this side. 1 minus x square times y1 equal to e to the m to the power of sine inverse of x. Now e to the power of m sine inverse of x is nothing but y. So square root of 1 minus x square y1 equal to my. Now to remove the square root, squaring. So 1 minus x square y1 square is m square y square. So let's differentiate it once more. 1 minus x square as it is. Now we differentiate y1 square, so that becomes 2 y1 y2 now, plus y1 square remains as it is and we differentiate the other. So minus 2x is equal to m square 2y1, no, 2y1, 2y1. Okay, so now 2y1 is common to all of them, so let's divide it by 2y1. So 1 minus x square y2 plus, or rather minus 2y1. 2 is also not required, so y1 x y1 minus, let's bring it to this side. Now 2 and y1 will go off, so we are left with m square y equal to 0. Now we can apply the Leibniz theorem. So nc0 yn plus 2, 1 minus x square remains as it is, plus nc1 yn plus 1, reduce it by 1 and differentiate 1 minus x square. So minus 2x plus nc2 yn times minus 2. In the next term it will become 0. Minus 2 differentiate 0. So the term will become 0. Plus, now we have to do it for this. Not plus, minus nc0 yn plus 1x plus nc1 yn times 1 plus, no, minus m square yn equal to 0. Now simplify. nc0 is 1, yn plus 2, 1 minus x square plus n times, let's do it in one step itself, minus 2xn yn plus 1 plus n times n minus 1 by 2 times, let's make this minus 2, so 2 gets cancelled, yn minus nc0 is 1, so xyn plus 1 minus n times yn minus m square yn equal to 0. So 1 minus x square yn plus 2, let's take minus out, xyn is common, so 2n plus 1 xyn plus 1. Now here, okay, n square plus n minus n plus m square yn equal to 0. And finally 1 minus x square yn plus 2 minus 2n plus 1 xyn plus 1 minus, these two gets cancelled out and we are left with n square plus m square yn equal to 0. And that's what we had to show. I think enough for today. Bye for